Okay, so hello everybody. It's week 6 of the Python DeCal. Today's Monday. I hope everybody's doing well. We have a lot to cover today, so I'm going to kind of speed through this. Long story short, we're going to be covering all the really useful stuff for data analysis. In particular, root finding. We'll be covering curve fitting, and then on Wednesday we will be covering numerical differentiation and numerical integration, which are all super useful. It's very sciencey, mathy, so you're going to use this very much if you go into research and or a lot of homework assignments in the upper division classes in astronomy and physics both use this. So hopefully this will probably be like really useful for you as you go forward with your major. I'm going to post the attendance link one more time in the chat, and then I'm going to go ahead and move on. Yeah. So announcements. Office hours are important. Please come to them. So far, nobody showed up to a single one of my office hours. So I don't know. I would appreciate if somebody come, or maybe we're just that good at teaching. I don't know. I don't know what it is. Attendance. Here's the attendance form. I've already put it in the chat. I'm gonna put it again as I hear more people coming in. But here's the attendance form for those watching at home asynchronously. I have a lot more announcements though. First and foremost, whoa, what happened? Sorry about that. That's weird. Let me exit and then read. Okay, there we go. So final projects. These are coming up. I mean, we have 6 weeks until they're like due. So, I mean, it's not like immediate, but it is important to know that they're on the horizon and we're going to start making you guys think about them and start doing stuff for them. So just keep that in mind. I put a quiz up on B courses. It's really a survey. It's not really worth anything for your grade, but I needed to have it up there so that you guys can, so that we can prepare you with lab partners and or project partners, or if you want to work alone, let us know and we can make that happen too. Your final project proposal will be due on March 15th. That's the Monday before spring break. Please don't forget about that. I don't think you'll be able to forget about it because we're going to bitch about it all the time until everybody gets everything in. But I need you to fill out that quiz that I mentioned by this Friday, the 5th of March by midnight. Because we're going to be putting you guys into groups and or partners and or single person groups over the weekend. And we want to make sure that you guys can all do that. It's under the quizzes tab on the B Courses website. Everybody should have gotten a notification for it. I made an announcement about it. So please check that announcement when you get the chance after lecture. But yeah, so please fill out that quiz by the end of the week. And then we also have special topics form. I sent this out at the beginning of the semester, but only 4 people answered it. Here it is right now. I will copy here. I will copy this link address and I will put it in the chat. Hopefully it works. Yeah, there you go. So that link I just put in the chat, that is the special topics form. It's a Google form. Just letting us know what you want to see, specifically which lecture types you want to see. We have lots of different options. We have, machine learning, many body simulation, observational astronomy, game writing, stuff like that. We have tons of different options for you if you want to see. A lot of them are listed on that form, and just let us know what your interests are so that we don't give you something that nobody wants to see. So yeah, those are all my announcements. Is there any questions about announcements? Okay, I will take that as a no. And just as a last announcement, I guess I would say, it's always appreciated if you turn your camera on, but you don't have to if you don't want to. It just makes it feel more like a classroom, and I'm always appreciative of it. So if you want, turn on your camera, but you don't have to. So we're going to recap. What are some examples of parameters we can put into the plot.plot function or plt.plot function? And then what types of plots other than plt.plot and plot.scatter can you plot with matplotlib? So we're going to do breakout rooms for this. We'll make 2, maybe, I don't know, there's a lot of people here today. Maybe, I think we can do 2 breakout rooms. We'll make 2 breakout rooms and you guys can discuss, chat with each other about the 2 questions. Again, what are some parameters you can put in the plot function, and then what are other types of plots you can make other than just the plt.plot and the plt.scatter, and what are the differences between them. So those are our 2 questions for the breakout rooms. I'm going to go ahead and make them right now. My 2 breakout rooms. Okay, and I'll see you guys in a couple minutes. Started recording like 15 seconds early, and that's like the most awkward pause, just for anybody who's watching that. Anyway, okay, so I think everybody is back now. Great. Yeah, they're coming in right now. So would anybody like to volunteer to go ahead and tell me or answer either one of these questions or both? It's up to you, but I would love it if somebody could volunteer to answer this.
So for the first one, you could put in like basically anything to customize the graph. So like the color, like the line, the sizes of things, anything like that.
Perfect. Yeah. Like aside from the X, Y, or X comma Y, yeah, you could change the line width. You could change the color. You could change the marker type. That's great. Awesome stuff. You can, yeah, cool. And then, oh, and another one is you can add a label for like a legend if you want to do a legend. That's all outlined in the Ultimate Plotting Guide. And then does anybody want to volunteer for the difference between plt.plot and plt.scatter? Okay. If nobody wants to, that's fine. I will mention it. So plt.plot is used for when you want to make like continuous, or you don't want to basically have discrete data points like dots on your graph. You want to kind of have like a continuous function. You can put an argument into plot.plot to make it the same thing as scatter, but typically you want to use plot.scatter if you're plotting lots of dots or data points, and then plt.plot for like a function that you're that's like continuous that you want to plot on your graph. And then other types of plots, there's error bar plots like plt.errorbar that you can include the error bars on. You can do a plot.histogram. You could do IMShow to give you the 3D plot or like the multivariable plot, and so on. So there's several different options there. And there's many more polar graphs and stuff like that. But those are the kind of the main that I know and I use on a regular basis. So anyway, let's go ahead and get into it for today. Here we go. So we can plot data, and that's great and all, but plotting data doesn't really let you discover anything. It doesn't like, you're not going to get any Nobel Prize in life just being able to plot your data on a graph and not be able to analyze it, right? So we need to figure out how to analyze things. And we can do that by fitting the dots or the data with a curve, say a function. If your data looks like a straight line, well, what is the parameters of that straight line? Is it a slope of 1? Is it a slope of 10? Where's the intercept? That might be really important for indicating something about or some information about the system that you're analyzing, the boundary conditions, you will. This will let us know the general trend of the data as well as the statistical insight. So from curve fitting, you can figure out how well it fits the curve. You can, like I said, figure out the different parameters that fit the curve and what they mean, their physical intuition. You can get errors on those. And you could do, from there, you could do error propagation for anybody who's taken like 5BL or 5CL or the 7 lab series. Typically, you have to do some error propagation, and you can keep error propagating, and you can find errors based on your data with curve fitting, which is great. It's always great. You learn a lot about your physical problem or your data set just by curve fitting. So what do we need for it though? So you need data and a model. Your model could be any function. It could be multivariable function. It could take in many function or parameters. It could take in one parameter. But it does need free parameters to be able to mold or to move around and check to see how well it fits. So typically, if you have a straight line, you're going to need some sort of coefficient out front plus another coefficient to help fit that line to any boundary curve. AKA, you need to be able to change the slope and you need to change the y-intercept to be able to fit any straight line. So the easiest way to curve fit any function or any data set, if it looks smooth and continuous, is usually with a polynomial. Think Taylor series, right? Taylor series and other polynomial expansions and stuff like that. So, I mean, we've seen this from calculus, right? You can add like a 0th order plus a 1st order plus a 2nd order and so on. And if you add enough of those polynomials together, you can actually approximate the actual function that you're looking at. So there's a function from the NumPy library that's super useful for this. It's called np.polyfit, and it's pretty self-explanatory. It takes in some x and some y data, and then the degree of the polynomial. So 0 means like a constant, 1 means like a line, 2 means a quadratic, and so on, so on, so on. Degree of your polynomial. And then it outputs an array of all the coefficients. So, I mean, it'll give you A0, A1, A2, and so on all the way to AP. And that gives you like a continuous polynomial. But you don't always want to do a polynomial. Sometimes you want to get into something a little bit more complicated. Sometimes you want to use other functions, and we'll talk about that in a second. But to talk about that, to talk about how you can fit other functions, we need to first talk a little bit about chi-squared. What is it? Well, take a stats class to really understand it, but it basically determines how well your data fits a curve. And you're trying to minimize this chi-squared value. Here, it's like basically it's like the sum of the error between your data point and the fitted model. So if your line goes through, let me do my laser pointer. If your line goes through this entire data set right here, right, it takes every little dot and it calculates the distance between that dot and your function, and it takes like the uncertainty in your data, of course, and it adds up all of those in quadrature, and it minimizes it. It's trying to find the line or the model that gives you the least amount of this chi-squared, this quantity right here. It minimizes that, and that's how standard curve fitting works with SciPy. And we'll talk about what that is in a second. But yeah, and then you should always be aware of overfitting. So make sure that whatever data set you're fitting, it has many, many more data points than the numbers of parameters you put in. And we'll talk about the parameters a little bit more, but the parameters are those degrees of freedom that can be changed in order to make your function fit the data better. Think of an example, the slope of a line and the y-intercept of a line, right? Those are your two free parameters. And you definitely don't want to have two data points to fit two parameters. I mean, it can work because it's a line, but for a much more complicated function, say you have 10 parameters, that's definitely going to be a no-no. You don't want to do that. You want to have lots and lots of data points to do this with. Cool. Is there any questions about this so far? Okay. Cool. So now more complicated functions, right? We want to be able to fit, maybe you have like something that looks like a Gaussian function. Maybe you have something that looks like an exponential. Maybe you have something that looks like a sine wave. You want to be able to make custom functions to fit based off of your theory, right? So we're going to import a library module. We're going to use SciPy to optimize. And we're going to import it in a little different way. We call it like this. We say from this library, SciPy to optimize, import a specific function, because we really only care about one function out of this whole library. So I'm just going to import it like this. But you can always just import it as an alias. Usually people use like fitter as the alias, so as fitter instead of as np for NumPy for NumPy. We usually use as np. This would be like as fitter or something like that. Doesn't really matter. It's personal preference. And then importing this function this way, lets you use just use that curve fit function without having to use like the dot notation that we talked about for so long. So yeah, it pulls out that function. I want to ask a question. Feel free to either type this in the chat or speak it out loud. I would love it if somebody answered this. What do you think we need, or what are we minimizing here to curve fit? Like, how are we going about this curve fitting business? I said it on the last slide, but I want to make sure everybody's paying attention. When we go to fit a line or a function to a set of data, we're trying to minimize something to make sure that that line is the best line, or that model is the best model that fits our data. Can anybody tell me in the chat? Yeah, chi-squared. And chi-squared is basically telling you like the distance between, it's like calculating or minimizing the distance between every data point in your model in a plot. Cool. Glad you guys are paying attention. Sweet. So this curve fit function, how do you use it? Well, here it is. I'll kind of put everything out. Yeah, well, we don't need to talk about that so far. So this is the curve fit function right here, scipy.curvefit, but we just, or scipy.optimize, we're importing the curve fit function. So this is the curve fit function. It takes in some model, which is a function. It takes like an f of x, right, that you define yourself. It takes in some x data, some y data. Then it takes in like an initial guess for every parameter in your model. And then it takes in a list of all the errors, like the uncertainty. Usually you have uncertainty in your data. Maybe that's like systematic error from like your measurements. Maybe that is other sources of error from 5BL that I don't really remember every single name of. But there's lots of different sources of error that contribute to error bars in your data. This is where you put that in, your Y error bar. And then you can also include X error data, but usually we just include the Y error data. And then we need to you can set bounds for where like what your like a fixed range for your like fitted parameters. So you can specify like it has to be within this and this. It can't be like above this or whatever, this value. Yeah, so under on modeling functions. So here's like an example of a model function, right? We call it a model function. This is the name of our function with a def statement. And then we see that x, like this is kind of like the independent variable. This is different than a parameter when you're fitting a model. X is like the independent variable when you go to plot. And A1, A2, A3, now these are your parameters. These are like your free parameters that can change from your curve fit. In fact, this function, what it's doing is taking all of these different parameters and it's playing around with them, tweaking it, kind of like, saying, oh, what happens if I make A1 -1? Well, what happens if I make A1 -1.1? And so on. And it does that with all the parameters based off of your initial guesses. And it finds the set of 3 parameters that minimizes that chi-squared value, aka minimizes the distance between every data point and the model itself. So that's what's going on there. And then the fitted parameters can be attained. Well, it spits all of it spits about a bunch of information to you in the form of basically it's like a list of 2 items. This fit params is actually a list. So the 0th component of that list is actually like the parameters. It's like a list of parameters. And then the second one is like a covariance matrix. And I'll show an example of how to pull out the errors on all your fitted parameters, as well as what the values are of the parameters in an example and demo. Yeah, so that's curve fitting. I know it's a lot, and we'll do a demo at the end of all this. I just want to kind of rush through the lecture material just to make sure we can do the demos. But is there any questions about curve fitting? Okay, I'll take those as a no, but please feel free to type it in the chat if you have any questions. Just let me know. Just as a recap, curve fit is a function from SciPy, which is a library, just like NumPy. It takes in a model, takes in your X and Y data, it takes in a list of guesses for like each free parameter. That would be in this model, that would be A1, A2, and A3. You would need a list of 3 different values that are guesses for A1, A2, and A3. And then you have your Y error list. Basically, it should be the same length as Y data, and it should be the error bar for every single Y data point. And then you can have bounds. That's optional. You don't really need the bounds. But yeah, that's the most important thing for curve fitting data. This will spit out a list of two index values. The 0th one is the actual. It's a list of the actual fitted parameter values, and then the second index of the list is actually, or the first index of the list gives you the covariance matrix, which you can pull the errors out of. And for anybody who's taking stats, then you know that the covariance matrix, the diagonals of that matrix correspond to the errors of each different, well, I think it's like the diagonals squared or something like that. We'll talk about it at the demo at the end of it, of lecture. But now we got to talk about finding roots. This is equally as important. Well, I wouldn't say equally. It's still really, really important, but I haven't had to use it nearly as much as curve fitting in all my classes and or research. But finding roots is super important. It's used all over the place. Anytime you need to find a root this is super useful to be able to do it numerically. So there are equations we simply cannot solve analytically by hand. Like a lot of you may have heard, like the three-body problem is typically like a perfect example of that. It's really hard to solve the three-body problem by hand. In fact, nobody's done it, at least as far as I know, like a general one. So we can do it numerically pretty easily, though. So we're going to use another function from scipy.optimize. We call it root. It's called the root function. And literally all this does, it takes in a function, like the root function from SciPy, takes in like whatever function is that you want, and then an initial guess, and it spits out the root. It's like super, super easy. So taking a function, I don't know, square root of 1 minus x squared minus sine of x, you want to find the root of these two functions, or like what this equals when they equal each other, or you find what that x, and the solution can be obtained by just doing sol.x. Super, super simple. I mean, it's just like you call it on a function, and you have an initial guess. Usually you find this by plotting the two functions, what the x naught might be. Yeah, cool. So we can also use this function from SciPy to optimize. Another function that does a very, very similar thing. In fact, I prefer using the fsolve, but I think there's like 7 or 8 different functions that all use or find roots in different ways. They're all pretty good. Some of them are used for slightly different scenarios than others, and that comes to Googling and looking up different functions, or taking Physics 77 if you want to know a lot more different types. There's like bisection method and secant method and Brent method and so on. It doesn't really matter. The two that we use the most are usually fsolve and root. So SciPy to optimize import fsolve, literally taking a function, taking a guess. If you want, sometimes you have some extra arguments, but really it's just usually taking function and a guess for what that root might be, and it'll spit out roots for you. So if you're getting this function for the first time, we're not going to do the breakout rooms because I don't think we'll have enough time for that, including my demos. So we're going to kind of not do breakout rooms right now, unfortunately. Yeah, so here's a little bit more explicitly written out. Here's the fsolve function. Func, it stands for just like any callable function that you've made. Usually it's one that you've made yourself. It could be like a 6th-degree polynomial. It could be a Gaussian function. You name it, doesn't really matter. And then x naught is the starting estimate of the root. So usually if you know your root's going to be somewhere just from plotting, right? Like let's say you plotted like a quintic or a 6th-degree polynomial on your x and y axis, and you see it kind of crosses the x-axis around 7, maybe 7.5 or something, but you don't really know what that number is. Well, that like 7 would be your guess, right? That would be your x naught, and so on. So yeah, and then args is any other arguments that goes to the function that you have defined, and then outputs. This all outputs like an array that contains the solution. So it could be an array of 1 value, 2 value, 3 value, 4 value, many value. Doesn't matter how many. It depends on how many roots your function has, but that's that. That's finding roots with fsolve. It's not super, super complicated. It's just a function that takes in another function and a guess, and it tells you when that function equals 0, basically, which is great. So that is everything. Yeah, I don't think, well, we might actually have time to do the breakout rooms again, although I don't know if I want to do breakout rooms twice. Well, I guess we'll just talk about this together. What if you are given this function for the first time, this np dot square root of, or square root of 1 minus x squared minus sine of x. Go to breakout rooms and discuss with others and come back with the explanation. Yeah, okay. So I'm going to alter this. Let's just say I want anybody who wants to answer this in the chat, just to like make sure that you're listening and paying attention. I guess I would say, if we put in a third degree polynomial, say ax cubed plus bx squared plus cx plus d, whatever, generic, it doesn't matter what that polynomial, what all the coefficients are, just know it's a third degree polynomial. And I want you to, or can somebody tell me how many elements in the, like, will the fsolve spit out in an array, right? So we know it will, if you take in that function, you give it some guesses for x naught, it will spit out an array, but can somebody tell me how long that array would be? Feel free to type it in the chat or speak out. Okay, I'll take it as nobody knows. If nobody wants to respond in the chat, that's fine. So let's just, maybe I worded this question pretty crappily. So let me say it again. So say we have a function, a cubic function, right? So any cubic function, any n degree polynomial has n roots, right? So a quadratic can have 2 roots, like a line usually has 1 root. A cubic root will have, or a cubic function, a third degree polynomial will have 3 roots, and so on. Just whatever n degree it is, it'll have n roots, likely. I mean, it doesn't have to, but I'm just saying it will. So if that's the case, we have a third degree polynomial. If you put in a cubic function, third degree polynomial in here, it should spit out a list of 3 values, 1 for each root. Okay? Cool. Yeah, okay, cool. And similarly, if it was a quadratic, it would spit out 2 values, whatever you name it. Yeah, so that's that. Now let's go ahead and move on to some actual examples that I think are a lot more interesting than just learning what the functions are. So I'm going to do a new share. I kind of have it all ready to go. So can everybody see this Jupyter notebook? Also, is it big enough for everybody? Is, like, should I zoom in a little bit more? Please write in the chat, let me know. Okay, cool. Great. So, yeah. So we have, this is our import statements, right? We're going to just import NumPy, matplotlib, and then also we're going to import the curve fit function from lecture that we talked about. So let's just say I have a data file. I call it variable star.csv. It just has some data in it. It has an x data, y data, y error data. This underscore, ignore it. It's just a formatting from the file itself. I just wanted to ignore that column. But so basically, we take the x data, the y data, and the y error data using np.loadText from the CSV file. Remember, set delimiter equal to a comma because it's a CSV, so everything's separated by a comma. And then we set unpack actually equal to true here because I want to take every column in my data file and I want to assign that to a different list or a different array, a 1D array. And then I'm going to skip the first row just because that's the way the file's formatted. In fact, I could show what that first file, or what that CSV file looks like. Just give me 1 sec. It would be DeCal demos variable star. So we, like, this is why I skipped the first row, because I don't care about these like words. I just want the numbers. And then that the reason why I did like an underscore comma is because I didn't want all these, sorry, it's really tiny. I didn't want the indexes. I don't care about the indexes, but I did care about the values. So Anyway, so that takes all that data and it puts it into an X data, Y data, and a Y error data, or like a 1D array. And now we can plot it. So let's go ahead and run these different cells. So I'm importing my statements. Let that star go away. There we go. We'll import the data. And then now I'm going to plot the data. I'm just going to plot an error bar function, ax.error bar. Remember, this is the object-oriented approach, not the state machine. So it's like the same thing we did for the subplots. I just wanted to mix it up, make sure you guys see an example of the other version, the object-oriented approach. So we have, figure axis, and then we just say we're just doing a bunch of things. We're inverting the y-axis because that's just how the data is. It makes it look nicer. I just know that because I've seen the data before you have. And then we're going to do error bar where it takes in X data, Y data, the Y error, and then some other arguments. And then we have Y label, X label, and so on. And then we're going to plot.show for an ending. And this is actual data from a telescope. In fact, this is from my own research group, Raphael and I's research group, variable stars. And what you're seeing right here is the magnitude versus the phase of a star that pulsates in brightness and size. And I believe this is an RR Lyrae AB star. So it's getting brighter and brighter, 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 and then it dims and dims and dims and dims, and then brighter and brighter and brighter, and dims and dims and dims. This is a phase plot, so it's technically not days, but this happens over the span of like maybe half a day or something like that. And the star is literally like pulsating at like, and you can see that with the light curve. And there's a lot of information to be learned about here. In fact, if you could figure out exactly how this light curve is shaped, you can actually learn a lot about the star. You can figure out how hot it is. You can figure out how much metal is inside of it. You could figure out the surface gravity on it, and so on. So there's a lot of interesting information to pull from just this one data set, but you need to know how the curve changes with phase. You want to know that. You want to specifically know exactly how it works, and you need a model to fit to it. So how do we do that? Well, some of you may have taken a couple more math classes than some others here, so I'll kind of elaborate what Fourier methods are. But a Fourier series is just a series, or like adding a bunch of sines and cosines with different parameters to it. And that's what we're going to do. We're going to fit a bunch of sines and cosines to this because it looks like sinusoidal, right? So that tells me that my theory should have something with sines and cosines in it. So I'm going to fit a bunch of sines and cosines to it and see what I can do. I'm going to start off though with just like a sine and a cosine and like another constant. And notice we're going to make our model. I call it f of x. It doesn't matter. I could have called it model. It doesn't matter. X is the independent variable going into our function, but A, B, and C are all free parameters that can change based off of the curve fitting function. And here we're just going to multiply every term by, or like the sine and the cosine by their respective parameters that can change. And then we're just going to add like an offset term here, C. So something that Fourier analysis tells us, or Fourier series tells us, is usually the more sines and cosines you add to your function, the better it fits the data, the more accurately it can, or precisely. So we know just adding like a sine and a cosine is not going to fit this data very well, but it's good to just start with the basics and then build up from there. And I'm going to just set like, I'm just going to say this, oh, this is not important. We don't even need that. About that. Anyway, so we take in we make a parameter guess array. So this is just like a list of guesses, right? I'm just going to say that I think A is going to be 1, I think B is going to be 2, and I think C is going to be 16. Just because C is the offset term, so it's going to be something like up here, right? It's going to be like, I don't know, it's got to be somewhere around between 16 and 15. So like, I'm just making random guesses. And the reason why you need those guesses, because if you just put like a billion or something, it can mess up the function. And for complicated reasons, that's not important. I don't really need to go into that. If you're curious, please ask, but it's not super important to understand how this works. We have the curve fit function, right? We're going to call it. It takes in our function, which has the free parameters. It takes in X data, Y data, the guesses, right? Par 0 is like my guess array. And then sigma is equal to the y error. Okay, and it'll spit out two things. It'll spit out a list of parameters, and it'll spit out a covariance matrix. And the way you access those, each parameter, if it's formatted in the way A, B, C, then, or like if your function takes in like in order A, B, C, then the 0th component is going to be your A. The first component of the parameter spit out is B, and second is C. And then to get the errors, you take the diagonal components of your covariance matrix and you square root them. And that'll give you A and the error on A, B and the error on B, C and the error on C. If this is a lot, which I'm sure it is, don't worry. This will be on your homework with like lots of step-by-step examples with a quadratic function and a linear function so that you get a hang of it with just some polynomials. And then you'll use it to fit something a little bit more complicated. So don't worry about it too much. Just know that I'm using this curve fitting function, takes in a bunch of stuff, spits out the guesses on your parameter, or it spits out what the best parameters and the best errors on those parameters are to best fit whatever it is your model is to your data. And then I'm going to go ahead and just plot that. And I'm just going to plot those specific error or like those specific parameters that the curve fit function gives me into my f of x and see what it does. So it's probably not going to be that great, but we can see what it looks like. Yeah. So right away, it looks pretty awful. It doesn't fit it correctly because it's literally only one sine and one cosine term. So it makes sense that it's going to be kind of garbage. But you can see the C parameter is actually 15.808, which is, that's the offset, kind of like the y-intercept, right? That actually is in the right ballpark. And then if I feel like if I add several sines and cosines to this, maybe it might get a little bit more sinusoidal, or maybe it might get a little bit bigger in amplitude and so on. Yeah, and if you add enough sines and cosines, it'll actually look like this. And this is actually from data. This is actual research that we do. This is what the curve fit should spit out with, I think, five sines and 5 cosines or something like that. And you actually see a light curve like this. And from this, you can actually learn a lot about information from the star. In fact, you can figure out that it has like a surface temperature of 6,800 Kelvin or something, just from this curve right here and the period and stuff like that, which is really cool. And then I want to give you one example on root finding. So this is a real life practical example that you might actually be able to, or like that you might actually need if you were going into doing research or whatever. And this would be like finding Lagrange points, for example. So it's known that if you look up, like some of you may have done this in 5A, if you took 5A or your mechanics class, or 105, if some of you are in 105, you can actually derive or like find a relationship that takes into account the Earth, the Moon, and the Sun, the 3 gravitational bodies. It's a 3 gravitational body problem. Remember how I said there's no closed form analytical solutions to the 3 body problem, but there are numerical solutions. In fact, there's 5 solutions to this problem where it's stable, right? And those are actually called the Lagrange points. Meaning if you were to put a satellite or some object at a Lagrange point, any one of these 5, sorry, it's kind of, there we go. If you were to put a satellite at any one of these, L1, L2, L3, L4, L5, it would be stable there and it would just be chilling and it wouldn't be getting sucked into anywhere. It would just be relaxing at this Lagrange point. So it could be pretty useful to find where those Lagrange points are relative to Earth, right? Figure out how far away they are. And this is like a nice diagram, kind of like space-time, I guess you'd say, showing like the fabric or whatever and where those Lagrange points lie. So let's find the distance to this L1 point. I think this would be a useful exercise and a good problem. And the way you do that is you would root find this function here. This is, I'm not going to derive this. That's a mechanics class. I don't care about that. What I do care about, though, is that this solution has five roots. It's a quintic equation in R. You can read about it right here. I can post this to anybody who wants it. But regardless, I'm just going to import a root finding function. This one I happen to use, it's one called bisect, but it does the exact same thing as fsolve. It does the exact same thing as root find, or I mean fsolve, or root and fsolve. It all does the same thing. It's just a different method. that the computer calculates itself. And I'm just gonna make an L1 function. This is like, I'm literally just copying this function and I'm putting it into my own coding function. Of course, defining all my variables, or unit quantities, constants, and then I'm just making a guess. I'm making some guesses, and I'm searching for solutions between 1 and like r minus 1. Anyway, it spits out the root of L1 from this root finding function. Okay, and we can run it just to show you. And you can find that it gives you what, 326,000 kilometers away. So L1 is 326,000 kilometers away from Earth using this bisect root function, which literally is like the exact same thing as the other root function from the slides, as well as the fsolve function. They all do like the exact same thing, just slightly different syntax. And if you were curious, you could look up bisect SciPy function and you can find the documentation on it. But that is everything I have to show you today. So if there's any questions, please feel free to ask. But that is all I have planned. And then on Wednesday, we will be talking about differentiation and integration. And yeah, and please get your final project poll in by Friday. I would really appreciate that. Yeah, thank you.
Thank you.
Thank you.
Thank you.
Thank you.